All right, everybody, welcome back to the final review video. This is the three of three. I thought it was only going to be two, but we will have a third. And we are going to pick up on a Michael conjugate addition as well as Robinson annulation. So Michael is another named reaction. So Michael conjugate addition. And Michael is really a combination, in my opinion, of Claisen and aldol. So let's just kind of review, this is review now, everything we know so far. So we know aldol is a condensation reaction between either two aldehydes or two ketones or an aldehyde and a ketone, okay? And we had two different types of that. We had thermo, we had kinetic. They result in different functionalities. Here, the alpha-beta unsaturated carbonyl is the one that's going to participate in a Michael reaction. We also saw we had a Claisen reaction, or the Dieckmann, which is the intramolecular version of that. And there was no thermo or kinetic that we had to consider, but we knew that the functionality was some sort of beta keto ester. And that functionality will participate in a Michael reaction. When we combine a beta keto ester and an alpha beta unsaturated compound together, we call that a Michael reaction. Now, not every, what we're going to call Michael donor and Michael acceptor, is a beta keto ester or an alpha beta unsaturated carbonyl. They could look similar and therefore have similar reactivity. But I think this is a good, cue in your mind to have when identifying what a Michael donor and acceptor is. So now, let me just give you some example problems, and before we even push arrows or draw the products, let's think about what would be the Michael donor and which one would be the Michael acceptor. So if I gave you this reaction, actually let me start here. I subjected these two substrates to this ethoxy base. The Michael donor is going to be some sort of nucleophile. Obviously, donor means it's going to add into something. And then the Michael acceptor is going to receive that nucleophile. So here I see a beta keto ester. This looks like a Claisen product. And that's from Claisen. The reason I think this is going to be the Michael donor or the nucleophile is we talked about in the last video the acidity, the enhanced acidity of the beta keto ester functionality based off of the dual inductive effect that we see from two carbonyls. There is dual resonance stabilization here. So this is a nucleophile. We can exploit the acidity of that proton. And we see we have an alpha beta unsaturated carbonyl. So we know that the alpha beta unsaturated carbonyls come from aldol, specifically the thermoaldol. Okay, and this is Michael addition, and we saw this back in exam 1, but Michael addition is also known as 1,4 addition. Okay, and 1,4 refers to 1, 2, 3, 4, where you're adding at the 4 position. Okay, and that is the beta carbon. So we could also call this beta addition. And I'm also going to call this the boomerang reaction. That may not make sense right now, but it will make sense when we push arrows. So just keep that in mind. You're never going to forget it after you see a mechanism. But you can imagine that we are going to add in the nucleophile of the beta keto ester into the beta carbon of the alpha beta unsaturated carbonyl. Now, why are we adding into the beta position and not the carbonyl carbon that is also an electrophile? This has something to do, which is a little beyond the scope of undergraduate organic too, but it has something to do with something called hard-soft organic chemistry theory. And we have essentially here a soft nucleophile. We call this beta keto ester a soft nucleophile because that enolate is resonance stabilized. That negative charge is softer than just a full formal negative charge. Why is it softer? It's spread across this entire molecule via resonance. So a hard nucleophile would be something that has a full negative charge, like maybe perhaps, I don't know, like hydroxide. That would be a hard nucleophile because that negative charge is localized there. Hydroxide would preferentially add into another hard electrophile. This is a hard electrophile, okay? Because if we were to push those pi electrons up, we have a full positive formal charge there. Okay, so again, this is beyond the scope of the class. You don't have to know hard, soft, organic chemistry theory, but essentially I just want you to know that the beta-ketoester nucleophiles are soft, and then the beta position of the alpha-beta unsaturated carbonyl is also soft. So soft like soft. This is not a hard combination. This is a soft combination, okay? So that's why it's adding into the beta position. If you want to know more about that, please come talk to me. I would love to talk to you about this and give you some insight, but it is not tested and it's not going to be expected of you. Okay, so let's now push some arrows and, oh, sorry, let me just fill in some more words here. This was the Michael donor, and we'll call that MD, and this was the Michael acceptor, something that receives the nucleophile, MA. Okay, and we could see how those are tied to both Claisen and aldol potentially. Again, there are other types, so I just wanted to bring this back. We know that alpha-beta unsaturated carbonyls form from thermodynamic aldol, but we also know that we can form these alpha-beta unsaturated nitro groups. Okay, and we could have, you know, maybe this dicarbonyl species, and if I were to subject this to sodium ethoxide, we could imagine that probably this is going to be my Michael donor, this will probably be my Michael acceptor, and if I were to think about reactivity, I would think that this is my nucleophile that's going to add into this beta position, okay? Now I think that's enough to actually do some mechanistic arrow pushing, so let me give you a reaction example. Okay, so here, I'm basically giving you this starting material. I'm subjecting it to this alkoxy base, the sodium ethoxide. And then step 2 is introducing this alpha-beta unsaturated carbonyl compound. And step 3 is acidic workup and heat. So let's kind of push some arrows, see how this clicks together. So this is where the boomerang reaction is going to come into play. So let's fill in our alpha proton. We know those are even more acidic than when we started with aldol or Claisen. And we can deprotonate, you know, sufficiently at that alpha proton to form a nucleophile. So this is the product of step 1. Step 2 is this Michael conjugate addition. So let's see how that works mechanistically. So I told you this is a beta addition. So when we fill in alpha and beta, we can see mechanistically that that nucleophile adds beta. We exceed the octet, so we must swivel those pi electrons over. We exceed the octet yet again at that carbonyl carbon, and we have to push those pi electrons out. So to me, this is as if I was pushing a boomerang out. If I trace the mechanistic arrows, it goes boom, boom, boom. It kind of goes in series and pushes outward. So the result of that mechanistic transformation is a structure that looks like this. So let me make that bond a little bit clearer. Okay. And let's see, this is beta, alpha, this is O minus, and we're there. Again, let me just fill that all in. This was the beta, let me keep blue just for consistency. This was the beta carbon, this is the alpha carbon, and that's where we are. Okay, so step 3, we have acid and heat. So the acid serves as a protic source, so we can draw hydronium. Let me go back to black here. We could draw hydronium nearby. So now this is the collapse or the return of the boomerang. That alkoxide comes back down, we exceed the octet, we have to push these pi electrons out, we grab a proton, and we return the sigma bond density back to the hydronium to form water. So again, boomerang comes from, you know, we push the nucleophile in, swivel, swivel, and then collapse, swivel, swivel. Okay, so boomerang always comes back. So the result is this structure. Okay, so we formed this structure. Now, did we form a chiral center? We absolutely did. And I just want to point this out. This is a workup. This is not hydrolysis of the ester and decarboxylation. We would make that very clear. I would write minus CO2, and I would like specifically say probably like HCl, like a lot. Okay, if I wanted hydrolysis and decarboxylation, but we don't say that, so we just want to leave it at this structure. This was a workup, and we did form a chiral center, so keep in mind we would expect you to draw the wedge, the wedge, and the dash, so plus the other, I guess, plus other, plus minus, is fine, okay? There is no specific name I can give you for that functionality, but just keep in mind that we are clicking on at the beta position, okay? Let's try another example that doesn't quite look like the Claisen and aldol products, okay? So like I said, it's typically going to be a Claisen or an aldol product, but doesn't have to be. It could be something that looks similar. So if I gave you an example that looks like this, okay, and I gave you these reaction conditions, what is my Michael donor or my Michael acceptor? Okay, well here we have a dicarbonyl compound. It's not a beta keto ester. It's not really a Claisen product, but we do have a dicarbonyl. And specifically, the dicarbonyl is located such that we have an alpha proton flanked by the two of them, by one atom removed. So essentially, this looks like it could be a Claisen product. So that proton is probably acidic. It probably could be deprotonated in this fashion to form the Michael donor. So this is my guess for Michael donor. And then this is an alpha beta unsaturated nitrile. We have not seen a reaction pathway to make these in terms of aldol, but it looks like an alpha beta unsaturated carbonyl. Remember, the CN group is really just a carbon nitrogen triple bond, so another deficiency, and it's in conjugation with the alpha beta alkene. Okay, so this looks like it could be my Michael acceptor. So it would react very similarly. We can imagine the base, in this case, like I've already shown you, is the methoxy anion. It forms the enolate. So the result is this structure over here. And then we have beta addition, of course. That's what Michael addition is. So we hit the beta carbon and we swivel. Okay, so maybe I'll draw the pi bond here just for clarity. So we have carbon, oops. Let me choose colors here. Nitrogen. Okay, so we have attack into that beta position. We have to swivel this over. We form this kind of funky structure here. Let me draw the result. This is a 1, 2, 3. 1, 2. I guess it's going to be interesting to draw. Okay. So here, let's do this. 1, 2, 3. Nitrogen. Okay, so now at 2, there was a methyl group. Between 2 and 3, there's a double bond, and 3 and the nitrogen, there's a double bond. I know that looks a little funky. There's a carbon atom right there. And of course, this is minus. All right. So now the boomerang comes back down. We have methanol in solution. So of course, the nitrile, the CN group can reform. We grab a proton, we return the electron density to the methoxy group, and then the result is a structure that looks like this. Okay, and just to be clear on that, 1, 2, that's your third carbon. Okay, you didn't have to do the mechanism for this. We wouldn't expect you to draw the mechanism for this type of Michael addition with the nitrile specifically, but you can imagine it reacts very similarly. So my whole point is, would you be able to predict the product? That's something we would expect you to do, and we would want you to add 1, 2, 3 carbons. You're adding 1, 2, 3 carbons specifically from the beta position of the alpha beta unsaturated group. Okay, so that's Michael addition. There's one variation of this. This is specifically called Gilman conjugate addition. So again, we saw Gilman reagents back in Orgo 1. We saw them also at the beginning of exam 2 material. Gilman reagents can add into acyl chlorides. Those are the only to form ketones, excuse me. So we saw essentially something that looked like this, and we saw maybe something like this, and we were able to show that these add in nicely to form ketones from acyl chlorides. Okay, so keep in mind these were always done at -78 or cryogenic condition temperatures. It was always in a aprotic solvent such as ether or THF, and we were able to sufficiently form a ketone. So this is a 1, 2, 3 fragment from the Gilman. So that's a review. Now we're going to show Gilman reagents can also attack into alpha beta unsaturated compounds, specifically at the beta position. This is a Gilman Michael addition variant. So if I gave you a starting material that looks like this, and I subjected it to a Gilman reagent, so something that looks like this perhaps, and I always have an acidic workup with these basic organometallic compounds. But essentially, we have an alpha beta unsaturated carbonyl. That's probably my Michael acceptor. And my Gilman reagent is obviously a nucleophile. We know that this carbon-metal bond is the nucleophile. This is probably my Michael donor here. And then in this mechanistic fashion, we'll show that we can have that carbon-metal bond act as the nucleophile that adds beta. We exceed the octet, so we swivel and we swivel. So the result of that transformation is a structure that looks like this. Oops. This is a 1, 2, 3, 4 carbon fragment. 1, 2, 3, 4. And that 3 is where the methyl group was. And then, of course, we have, hydronium from step 2 to kind of pick up a proton. This is the end of the boomerang. So would you be able to predict the product in 2 seconds? I hope you can. It's just clicking on this carbon fragment to the beta position and removing the double bond that you saw of the alkene. So 1, 2, 3, 4, that's your structure. Did we form a stereocenter? Yes, we did. We would expect you to draw both of the tumors. All right, so that is that question. Let's think, I guess now we can go on to Robinson annulation. So Robinson is the very end of this material. So Robinson annulation, this is the last of all the enolate chemistry reactions we have seen. And Robinson annulation is essentially just one final step after a Michael reaction. So now we've seen, maybe I'll go back to the last page here. We've seen aldol, we've seen Claisen, we've seen Dieckmann. We've now seen Michael. So the result of a Michael reaction is just maybe, we'll call this a Michael product. And if we do one final aldol, we will get a Robinson annulation. Okay, and now a Robinson, sorry, that kind of cut out here. Let me rewrite this for you. A Robinson annulation. And just like we saw with aldol, thermokinetic, and Claisen, and we had these specific functionalities that were forming, such as the alpha-beta unsaturated carbonyl, the beta-hydroxy, the beta-keto etc. There's a functional group that we will always see with a Robinson. And typically, we have fused rings. It doesn't always have to be a fused ring, but specifically within one of those fused rings, we form a cyclohexene-one. Cyclohexenone. So if you see that in a synthetic problem, you probably had to go to a Robinson, which means you had to do a Michael and an aldol somewhere. Okay, so a cyclohexenone, and if it was bicyclic, would be a structure that looks like this. Okay, there's an alkene, a cyclohexyl group, and a carbonyl ketone. Okay, so let's kind of talk about an actual Robinson example. Okay, so it's just one step further from the aldol reaction. Let's think maybe something like this. Okay, so we have maybe this starting material. Okay, and I am going to do these as the reagent conditions. Okay, So clearly, I see I have what looks like a beta keto ester. This is a Claisen product, beta keto ester. This is a Claisen product. That's probably my Michael donor. Remember, we have this enhanced acidity. We can form a nucleophile at that alpha proton, and that's probably what's happening with this base over here, is deprotonating the proton, and then we were returning that electron density. Okay, so just keep that in mind. I think we're beyond that mechanistic depiction at this point. So once we see that we have a Michael donor, we have an alpha beta unsaturated carbonyl. This is probably, let me write that in, alpha beta unsaturated carbonyl. So this is probably, an aldol product, and specifically the Michael acceptor here. Okay, so we are going to form first a Michael reaction. Then we'll do that final aldol to show you how we form this kind of fused cyclic structure. So in terms of a Michael, I think mechanistically we should show that again. We would add into the beta position, we exceed the octet, we swivel those pi electrons over, and then the pi bond of the carbonyl gets pushed up. That's the boomerang. The result is a structure that looks like this. Let me just make sure I'm numbering everything right. That's right. Let me just count carbons here. We're attacking at 1, 2, 3, 4. We're attacking at 1, 2, 3, 4, and at 2 we had an extra methyl. Beautiful. Okay, then we obviously have ethanol hanging out in solution. So that, oh, and sorry, let me finish. The double bond was between, it looks like, now 2 and 3. Okay, so the O minus collapses back down. This is the boomerang coming back out, grabbing the proton for methanol, and the result is a structure that looks like this. Please take your time like I am on these problems, because we don't want you to like drop carbons or add carbons. Okay, so that is the resulting structure. I'm drawing the carbon-carbon bond kind of dramatically just because it's I need more space and these things have to connect together. And now we're going to show that, so we did a Michael reaction. This is the Michael product. Okay, so Michael product. Then there's one more step. Of course, we still have base hanging out in solution, so we could perform one final aldol, specifically an intramolecular version, if it formed a 5 or 6 membered ring. So let's see. Based on the group that we just added in, we have, a ketone, a pendant ketone, that I'm looking specifically at this position, and I see that I have 2 alpha positions. If I consider how both of these would add in, if I picked this alpha proton, it would add in this is carbon 1 of the ring, 2, 3, 4. We don't form 4 membered rings. If I picked this enolate, or this alpha proton, 1, 2, 3, 4, 5, 6. Oh, we have 6 members of the ring. So we can show on the next page, so maybe let me copy this and bring it to the next page. I don't know how to do that. Is that copy? Maybe? Okay, and then paste. Oh, nice. Okay. So from here, we still had base in solution. So let me draw in the alpha proton for some clarity. Okay, we can form the enolate at that pendant ketone. The result is a structure that looks like this. Okay, and now we're going to show it adding into the ketone on the ring. Obviously, we see the octet. We have to push those pi electrons up. So let's number this members of the ring. 1, 2, 3, 4, 5, 6. Let's draw a 6-membered ring. Fill in our numbers and fill in all of our substituents. So 1 attacked. Here, let's just do it like this. 2, there was a carbonyl. 3, there was a methyl. 4, there was nothing. 5, it seems like there was an ester, as well as a 6-membered ring. So let's kind of fuse that together. Okay, and at 6 is where we attack. So 6, we had an O minus. So this is the first, fused ring structure we have seen. Now we are going to form the neutral beta hydroxy compound. So that would be a result of having ethanol in solution. Okay, remember this is aldol. So we formed a beta hydroxycarbonyl first. That's kind of what we always saw. And then thermo went the extra step further, and we'll see that in one second. So we formed a beta hydroxycarbonyl, just like we saw with aldol. And if you can't see that, I'll point it out to you. This is the beta hydroxycarbonyl. Again, let me fill in our Greek letters here, alpha and beta. Okay, and again, if you couldn't see from the reaction conditions on the last page, we are subjecting this to heat. So heat is our cue to go the step further. It's thermodynamic. We want to dehydrate. So you can imagine that we're going to lose, at any given point, ethanol can also protonate this hydroxyl group. It will leave based on heat, and we have this alpha beta unsaturated carbonyl forming. So something that looks like this. Actually, I guess I could show you mechanistically. So we have ethoxide. Obviously, we're under basic conditions, so we can do this E2 elimination. And the result is this fused cyclohexene own structure. How do I know it's a cyclohexene own? Well, if I look specifically here, I formed a cyclohexyl ring with a ketone and an alkene. So I want you to be able to, draw these products. They look scary at first, but not too bad if you know your aldol chemistry and your Michael chemistry. But keep in mind, we did form 2 chiral centers, so we actually have 2 to the 2, or 4 major stereoisomers to consider. That would be the wedge, dash, dash, wedge, dash, dash, wedge. Okay, so that's the only nuance to Robinson. It's just one final one final aldol reaction after a Michael addition, and only when you could form 5 or 6 membered rings. Keep in mind that this type of chemistry won the Nobel Peace Prize for synthetic steroid synthesis for various medications like cortisone and whatnot. Forming these highly fused cyclic structures is very synthetically challenging, but once the Robinson annulation reaction was discovered, we could actually synthesize a lot of these steroids our own and not rely on nature to do that. And you could see the profound effect it has on medicine these days. So anyway, I think that's the good conclusion for enolate chemistry. I like this stuff. I hope you can understand it as well as me by knowing the interconnectedness of all of this. Watch these videos a couple of times. You guys will do great. I'm rooting for you. Have a good fall break. And as always, fight on. See you guys.